Picture yourself aboard a vessel designed not in fantasy, but in engineering labs. This spacecraft exists within the boundaries of physics we already understand. Its blueprints could be drafted today with existing knowledge and materials. Interstellar tourism remains beyond our reach for now, but every world orbiting our sun lies within theoretical grasp. Consider it a checklist of destinations scattered across our cosmic neighborhood. The question becomes not whether we can visit them, but how many years each journey demands. The answer defies simple arithmetic in ways that might surprise you. Navigating between worlds requires wrestling with forces older than planets themselves. We push against constraints written into the fabric of reality with nothing but metal and mathematics. Success depends on respecting limits while exploiting every advantage the universe offers. Our humble craft must operate at the edge of what physics allows. One miscalculation and years of preparation evaporate into the void. Before departure, we need something resembling a chart, though not the kind you'd use on Earth. Traditional maps fail completely when applied to solar system navigation, and the primary reason involves perpetual motion. Every object circles the sun in its own elliptical dance, moving at its own distinct velocity. No fixed positions exist here, only trajectories that shift with each passing moment. Earth races along its track at roughly 107,000 kilometers per hour right now. Jupiter moves differently, Venus differently still, Mars at yet another speed entirely. When we aim our spacecraft toward any distant world, we're not pointing at current locations. The target must be where that planet will arrive by the time we reach its orbit. Imagine trying to hit a bullseye painted on a spinning disk while standing on a different spinning disk. Now imagine both disks are invisible and separated by millions of kilometers of emptiness. Add the constraint that you get exactly one attempt with no second chances allowed. Miss your mark, and a decade of work plus hundreds of millions in funding simply vanish. This unforgiving accuracy requirement stems directly from our most precious resource in space: fuel. Think of driving with precisely enough gasoline to reach your destination using only the most efficient route possible. Any detour, any unnecessary acceleration, any moment of wasted throttle means you never arrive. Even driving slightly too fast or braking unnecessarily would leave you stranded short of your goal. That pressure defines every interplanetary mission we'll attempt from this point forward. To extract maximum value from our limited propellant, we must work alongside rather than against the most dominant force in existence: gravity. Unfortunately, before gravity becomes our ally, it must first be overcome as an adversary. Escaping Earth's gravitational embrace doesn't represent our hardest challenge ahead, but it certainly demands the most concentrated energy expenditure. Our rocket consumes fuel sufficient to fill an Olympic swimming pool every second during its 2-minute burn phase. Only then do we climb above the atmosphere and cross the invisible threshold into orbital space. We're now circling Earth at velocities exceeding 20,000 kilometers per hour, faster than the planet's own rotation. This speed allows us to effectively outrun gravity's downward pull and maintain stable circular motion. From our perspective aboard the craft, something peculiar begins happening that contradicts everyday experience. We're not steering around Earth like a car following a racetrack's curve. The ship flies perfectly straight from its own reference frame, while Earth's gravity bends the space itself. That warped space shapes our trajectory into a circle without any input from our navigation systems. The faster we push against gravity, the more fuel we burn, the straighter our curved path becomes. Greater velocity carries us further from the planet's surface into higher orbits gradually. Conversely, if we were to reduce speed now, gravity would tighten its grip on our trajectory. Slow down too much, and that tightening curve intersects with Earth's surface in a catastrophic re-entry. We must avoid that outcome, obviously, so we're going to double our current velocity instead. Accelerating to over 40,000 kilometers per hour relative to Earth finally breaks us free completely. We've now begun our true interplanetary voyage, traveling at roughly 150,000 kilometers per hour relative to the Sun. Our spacecraft has joined the billions of objects hurtling through space on their own independent trajectories. But freedom from Earth doesn't mean freedom from all gravitational bonds or constraints. The Sun's gravity holds us just as it holds every planet, asteroid, and comet. We're orbiting on a much grander scale now, with different rules governing our motion. Since most solar system objects occupy roughly the same flat plane, our directional choices reduce to essentially two options: We can travel inward toward the sun or outward away from it, with limited vertical freedom. Whichever direction we choose, our path will curve around the sun's gravity well in predictable ways. Remember that fundamental rule: no straight lines exist in gravitational fields, ever. We control our trajectory by manipulating velocity, speeding up or slowing down to reshape our curve. Wandering aimlessly would be relatively simple from this starting point, but reaching specific destinations and establishing stable orbits requires calculations of extraordinary precision and complexity. Understanding orbital mechanics through pure theory feels abstract until you watch your fuel gauge dropping with every maneuver attempted. Breaking free from Earth's gravitational field represents the single most fuel-intensive moment of any interplanetary mission we'll ever undertake. Our rocket must burn propellant equivalent to an Olympic swimming pool's volume every second during its initial climb. That 2-minute ascent through atmosphere consumes more energy than all subsequent maneuvers combined in many mission profiles today. We cross into space officially by achieving velocity exceeding 20,000 kilometers per hour faster than Earth's rotation. At this speed, we effectively outrun the planet's gravitational pull and establish circular motion around its equator instead. Now something counterintuitive begins happening that challenges everything ground-based navigation taught us about movement and direction fundamentally. From our perspective inside the spacecraft, we're traveling in a perfectly straight line without any steering input whatsoever. The ship doesn't curve itself around Earth like a vehicle following a racetrack's banked turns through deliberate effort. Instead, Earth's gravity warps the space surrounding it, and that warped geometry shapes our trajectory into a circle. The harder we push with engines against gravity, the faster we travel, the straighter that curve becomes. Higher velocities carry us further from the planet's surface into progressively higher orbits with each velocity increment gained. On the reverse side of this gravitational equation, reducing speed produces the opposite effect, with potentially catastrophic consequences ahead. If we were to slow down from our current orbital velocity, gravity would tighten its grip significantly. That tightening curve would pull our trajectory closer to Earth's surface with each meter per second lost. Slow down too much, and the curve intersects with atmosphere, then ground, in a re-entry neither planned nor survivable. We definitely want to avoid that particular outcome, so instead we're going to accelerate even harder now. Doubling our velocity to over 40,000 kilometers per hour relative to Earth finally breaks us completely free. We've escaped Earth's gravitational dominance at last and begun our true interplanetary voyage through the solar system proper. That puts our total speed relative to the Sun at roughly 150,000 kilometers per hour. We're now just another object hurtling through space, following our own independent trajectory around our star. But freedom from Earth's gravity doesn't mean freedom from all gravitational constraints or influences affecting our path. The Sun's gravity captures us just as thoroughly as it captures every planet, moon, asteroid, and comet. We're orbiting on a vastly larger scale now, but still orbiting nonetheless under rules that govern everything. Because the solar system's major objects occupy roughly one flat plane, our directional options reduce to essentially two choices. We can travel inward toward the Sun or outward away from it, with limited vertical freedom available. Whichever direction we choose, our path will curve around the Sun's gravity well in mathematically predictable ways, always. Remember that fundamental principle we established earlier. Straight lines simply don't exist in gravitational fields under any circumstances. We control our trajectory exclusively by manipulating velocity, speeding up or slowing down to reshape our curve. If our goal involved just wandering aimlessly through space, then this would be relatively simple to accomplish indefinitely. But steering our spacecraft towards specific destinations and establishing stable orbits upon arrival requires calculations of extraordinary precision. Every maneuver must be planned accounting for fuel limitations, gravitational influences, and the perpetual motion of target worlds. One wrong calculation, and we either miss our destination entirely or arrive unable to slow down sufficiently. The margin for error shrinks to nearly zero when operating under such tight fuel constraints we're facing. This is where mission planning transforms from theoretical exercise into life-or-death engineering challenge requiring absolute accuracy. Every trajectory adjustment must be calculated months in advance, and executed with split-second timing for success guaranteed. Testing these principles in practice seems like the only way to truly understand the challenges ahead now. So let's commit to our first destination and work through the actual mechanics of reaching it successfully. We're setting course for Mercury, the innermost planet orbiting closest to the Sun of all worlds. You might find it surprising to learn that Mercury represents the hardest planetary destination for us to reach. That difficulty makes it an excellent choice for our inaugural mission, since conquering Mercury teaches lessons applicable everywhere. If we can figure out how to get there successfully, then every subsequent journey becomes easier by comparison. In terms of pure distance, Mercury sits relatively close to Earth at roughly 80 million kilometers away. But it orbits even closer to the Sun at an average distance of just 58 million kilometers. Because Mercury occupies such a deep position inside the Sun's gravity well, it must travel incredibly fast. The planet races around at approximately 170,000 kilometers per hour to avoid falling inward. From our current velocity, we face two distinct challenges that must be overcome before arrival becomes possible. First, we need to slow down enough to begin falling toward the Sun instead of maintaining orbit. Second, we must control that fall precisely so we arrive at Mercury without overshooting or crashing catastrophically. From our position orbiting just beyond Earth, we need to reduce velocity by almost half initially. We're essentially undoing all the hard-won velocity we gained escaping Earth's gravity in the first place here. In this way, we're intentionally losing our battle against the Sun's gravitational pull and allowing it to bend. That curving pulls our path downward until it intersects with Mercury's orbital track around the Sun eventually. This maneuver sounds simple enough in theory, but it only represents the easier half of our challenge. Burning through another significant portion of our limited fuel supply accomplishes this much, but sets us up immediately. Now we face an even bigger problem that will test every limit of our spacecraft's capabilities going forward. Falling into the Sun's gravity well behaves exactly like rolling down an increasingly steep hill under acceleration. You tumble slowly at first, but the further you fall, the faster you go with each meter. In the context of the Sun's gravitational field, the closer you approach it, the harder it pulls. So even though we had to slow down initially to begin our fall, we're actually accelerating rapidly. By the time we reach Mercury's orbital distance, we'll be traveling at roughly 210,000 kilometers. This creates our central dilemma. We'll be moving far too fast to establish orbit around Mercury safely. The ship must slow down dramatically for a second time, or we'll simply blow straight past helplessly. How do we bleed off that much velocity without exhausting our fuel supply before even arriving there? This earlier mission, called Mariner 10, demonstrates exactly what happens when you arrive too fast without options remaining. NASA launched that probe back in 1973 using the falling down the hill method we just described. It reached Mercury in only 5 months, which sounds impressively quick compared to our planned multi-year journey ahead. But speed came with a critical trade-off that doomed the mission to partial success at best ultimately. By arriving so incredibly fast, the probe carried far too much velocity to slow down sufficiently. Mercury's weak gravity couldn't capture something moving that quickly, no matter what maneuvers the engineers attempted desperately. So Mariner 10 gathered whatever data it could while screaming past the planet at thousands of kilometers. The spacecraft became an unintended flyby mission rather than the orbital study originally planned by mission designers. In theory, we could just burn our engines again harder to bleed off all that excess velocity. That would solve our speed problem directly through brute force application of thrust against our forward momentum. But doing so would push our fuel requirements far beyond anything remotely feasible with current technology constraints. Hence the fate that befell Mariner 10, despite its engineering team's best efforts to salvage something. This is why only one NASA mission has ever successfully entered orbit around Mercury in history. That probe was called Messenger, and it launched in 2004 on a journey nobody envied. It took 6.5 years to complete the trip from Earth to stable Mercury orbit. The mission planners achieved this seemingly impossible feat by using gravity itself as their primary braking mechanism. The Messenger probe leveraged gravitational assists from Earth, Venus, and Mercury itself to achieve results equivalent to burning impossible. These gravity assists work by stealing a tiny bit of momentum from planets as you fly past. The planet's own orbital motion either speeds you up or slows you down depending on approach angle. Each encounter bends your trajectory without requiring any fuel expenditure from your precious reserves remaining on board. The massive downside is that it requires making multiple trips around the sun to line everything up. You're essentially taking the scenic route through the solar system to save fuel for final approach. Hence the multi-year journey that made Messenger one of the longest missions to a relatively nearby destination. But it worked where brute force would have failed completely, so we're adopting their proven strategy. Following the flight path laid out by Messenger, our first target won't actually be Mercury at all. We're going to aim for Venus instead, which seems counterintuitive until you understand the geometry involved here. The idea is that we fall toward the sun in such a way that we pass very close. Venus sits between Earth and Mercury, making it a perfect gravitational stepping stone for our purposes exactly. Our goal will be coming close enough that Venus's own gravity begins influencing our spacecraft's direction significantly. We call this maneuver a gravity assist because we're literally using planetary gravity to assist with steering. If gravity handles the directional change, then our engines don't have to do that work themselves. Less engine work means less fuel burned, which means we might actually arrive with reserves remaining for capture. In this specific case, we're going to approach Venus so its gravity pulls our trajectory upward slightly. We're still falling toward the sun, but now the hill isn't quite as steep as before. This adjustment allows us to fly completely around the sun and catch Venus again for a second pass. But this time we're coming much closer to the planet itself, within just a few hundred kilometers. That proximity allows gravity to bend our curve even more dramatically than the first encounter accomplished. This second gravitational kick sets us up perfectly for our first actual encounter with Mercury itself, finally. The Messenger probe that we're modeling our flight plan after had to fly past Mercury 3 separate times. Each Mercury encounter bent the spacecraft's path just a little bit more, bringing it incrementally closer to matching. With each successive flyby, gravity nudges our trajectory into better alignment with Mercury's own orbital path around the Sun. After the third gravity assist from Mercury, we're finally close enough to make one last course correction. We'll need to fire up the main engines again for the first time since beginning our plummet. We're going to time this burn so it slows us down right as we pass closest to Mercury. The small planet has relatively weak gravity at only about 1/3 the strength of Earth's pull. But if we can reduce our speed enough at precisely the right moment, then Mercury's gravity wins. It pulls harder on our ship than the Sun's gravity does at that specific distance and angle. The path of our spacecraft curves all the way around into a stable orbit of the planet finally. All of this assumes we have a bigger and more powerful ship than the original Messenger probe carried. We're also accepting that we'll need to perform similar rounds of gravity assists to lock trajectories in. We'll complete many trips around the Sun before we arrive at our final destination, as frustrating as that. The journey from Earth to Mercury using this multi-assist approach is going to consume about 5 years total. 5 years of coasting through space, making careful gravitational maneuvers to arrive at our closest planetary neighbor successfully. That timeline feels almost absurd when you consider Mercury orbits only 80 million kilometers away from us. But the tyranny of orbital mechanics and fuel limitations leaves us no faster path forward with technology. Now here's the encouraging news that makes the rest of our solar system tour feel more manageable afterward. Not every interplanetary trip has to be so elaborate and complicated as this Mercury mission proved. When we look at Venus, we see our closest planetary neighbor and our shortest trip through space. The journey there won't require years of gravitational pinball or multiple solar orbits to achieve success, fortunately. But that doesn't mean this voyage will be boring or without its own unique challenges to overcome. Venus presents different obstacles than Mercury, but they're obstacles we can actually solve more directly and efficiently. From our starting point just beyond Earth's gravitational influence, we know we need to go down towards Sun. That means firing up our main engine to begin killing off some orbital momentum and starting our fall. That initial burn is going to get us to Venus surprisingly quick compared to Mercury's timeline. In just about 4 months, the Sun's gravity will pull us down to the orbit of Venus. We'll arrive at the planet's distance from the Sun in less than 1/3 the time Mercury required. But just like with Mercury, we're now traveling too fast to be captured by planetary gravity alone. If we don't find a way to reduce our speed dramatically, we'll just sail right past helplessly. Fortunately, we have significantly more options at our disposal this time around compared to Mercury's constraints. For one thing, Venus is a much larger planet than Mercury, so its gravity has nearly triple. That stronger gravitational field gives us much more pulling force to work with for orbital capture maneuvers. And for two, Venus has an atmosphere which changes everything about our approach strategy and available options. It's very thick, almost 100 times more dense than Earth's atmosphere at sea level comparatively. By flying very close to the planet and touching the upper edge of that thick atmosphere carefully, we can actually slow down substantially just by using aerodynamic drag against our forward momentum here. The friction of atmospheric particles hitting our spacecraft at high velocity bleeds off kinetic energy as heat. By combining these two natural forces with a powerful burn from our main engine at periapsis, we can insert our spacecraft into orbit around Venus less than 5 months after leaving Earth behind. That's less than 1/10 the time Mercury demanded, making Venus our quickest interplanetary conquest by far and away. When it comes to reaching our next destination, Mars, this is where everything gets flipped around completely. We're flying away from the Sun for the first time, which means accelerating upward against gravity's pull. Instead of falling down a hill, we're now climbing up one, which fundamentally changes our fuel calculations. And yet slowing down upon arrival will prove even harder than anything we faced at Mercury or Venus. Spacecraft from Earth have flown to Mars dozens of times over the past 4 decades of exploration. It's by far our most visited planetary neighbor, making it almost feel routine in comparison to Mercury. American audiences know Mars through rovers like Curiosity and Perseverance that currently explore its surface right now. Those missions have developed a remarkably efficient method for getting there that prioritizes fuel conservation over raw speed. The technique is called the Hohmann transfer orbit, and it represents elegance in orbital mechanics at work. We wait until Mars and Earth line up on their closest approach around the Sun, patiently watching. That optimal alignment comes only once every 2 years, so timing your launch window becomes critically important here. During that narrow window, all we need to do is launch our spacecraft and accelerate just slightly. We only need to move a bit faster than our own planet travels in its orbit. That small velocity increase is enough to get us rising up and away from the Sun gradually. In theory, we could accelerate much harder and reach Mars in just a few weeks, potentially. But arriving faster would only create massive problems when we actually get there that outweigh any benefits. The issue stems from Mars being further from the Sun than Earth, which means it travels slower. Mars cruises along at roughly 86,000 kilometers per hour compared to Earth's 107,000. If we accelerate hard away from Earth right now, we're going significantly faster than Mars moves. That means we'll need to slow down dramatically by the time we reach Mars's orbital distance. We'd have to bleed off 64,000 kilometers per hour of velocity just to match the planet. Unlike Mercury, there are no convenient planets along the way for gravity assists to help us slow. And unlike Venus, there's no dense atmosphere around Mars to provide meaningful aerodynamic braking for our approach. Mars has a much weaker gravitational field than either Earth or Venus, which limits its capture ability. The atmosphere that does exist is less than 1% as thick as Earth's, making drag. So it's all about using the engines on our spacecraft and burning precious fuel reserves carefully. We have to get our velocity low enough for Mars's weak gravity to pull us into orbit. This is why missions take as long as 8 months to reach Mars, despite relatively close proximity. We could arrive much faster with harder acceleration, but we'd never slow down enough to stay. The spacecraft would just scream past Mars, unable to establish orbit, leaving years of preparation wasted completely. The 8-month journey to Mars has become standard operating procedure for NASA missions over the past decades. American teams have landed rovers, orbiters, and landers using this exact transfer orbit approach with reliable success. It feels almost mundane compared to the elaborate multi-year dance required for Mercury's gravitational assist sequence. But that familiarity shouldn't breed contempt for the genuine challenges involved in reaching Mars safely every time. Every launch window demands perfect calculations accounting for both planets' positions months in advance of departure. Every trajectory adjustment must be executed with split-second precision, or the mission fails catastrophically without recovery. The comfort of routine masks the underlying difficulty that still defines interplanetary travel under current constraints. Now, Jupiter is where things start to get really interesting, because we're going deep into space. You see, Jupiter sits 5 times further away from the Sun than Earth, which means serious distance. That gulf means we can't simply hop from one orbit to the next like we managed for. Instead, we return to the gravity assist technique that guided us down to Mercury's challenging orbit earlier. On that flight, we leveraged Venus's gravity to curve our path down toward the Sun beautifully. All we need to do now is switch up our approach angle and use planetary gravity. We can actually use Venus to fling us out on a path straight toward Jupiter instead. Once we're on our way, coasting through space, we now have 2 distinct challenges to consider carefully. One is crossing the asteroid belt, which sounds terrifying if you've watched any science fiction movies. This region between Mars and Jupiter contains hundreds of thousands of rocky objects ranging from dust grains. These range up to asteroids the size of small moons, all tumbling through space chaotically. At the velocity we're traveling right now, even getting hit by a very small rock means the impact would have catastrophic results, destroying our spacecraft and ending the mission instantly without warning. If we were in a Hollywood blockbuster, then this would be the nail-biting sequence with dramatic music. But in reality, it's mostly empty space out there, despite what movies suggest to audiences everywhere. The rocks are so spread apart that you could fly through the belt 100 times. Statistically, you'd never come close to hitting a single one of them during any of those passes. The asteroid belt sounds dangerous, but it's actually one of the safest parts of our journey. So after crossing through the asteroid belt without incident, we meet our second challenge, which is Jupiter. This planet is humongous, beyond anything we've encountered so far, making previous worlds look tiny in comparison. It's 2.5 times more massive than every other planet combined, which is difficult. That enormous mass means the force of gravity around Jupiter is equally as powerful, almost like orbiting. Which means, just like the Sun, Jupiter's gravity starts pulling us in as we approach its domain. So we transition from climbing up the hill of the Sun's gravity to falling down Jupiter's. That definitely helps us get where we're going faster by accelerating us toward our destination efficiently. But it also brings back an old nemesis we thought we'd escaped after leaving Venus behind. You guessed it correctly. The problem of slowing down returns with a vengeance at Jupiter's orbit. Out here in deep space, far from the Sun's intense pull, everything moves at a relaxed pace. Remember Mercury racing around at 170,000 kilometers per hour back in the inner system? Well, Jupiter cruises at about 47,000, which feels almost leisurely by comparison to inner planets. Our spaceship is traveling over 5 times that speed right now, after our long acceleration outward. So we've got serious work to do, bleeding off all that excess velocity before capture becomes possible. The power of Jupiter's gravity is simultaneously a blessing and a curse for our mission profile. On one hand, it pulls us in and makes us go even faster as we approach. But because the gravitational force is so powerful, it can bend our path into an orbit. It can capture us even when we're outrunning the planet itself at seemingly impossible velocities overhead. So we don't have to take our speed all the way down to match Jupiter's slow progression. We only have to bleed off enough velocity to get caught in its deep gravity well permanently. When NASA's Juno spacecraft approached Jupiter in 2016 on a path similar to ours today, carefully, the probe had to burn its main engine for 35 minutes straight just to lose speed. After falling toward the Sun, speeding up, looping around Venus, getting flung into deep space magnificently, after crossing the asteroid belt, falling into Jupiter, and slowing down again, it's taken us 3 years. 3 years of careful navigation through the solar system to arrive at this gas giant's doorstep. And now the real fun is about to begin as we unlock the outer solar system. Now here's a really fun question that opens up the rest of our solar system for exploration completely. What happens if we don't slow down at Jupiter, but instead maintain our current velocity through closest approach? Well, the answer becomes how we unlock every remaining world in the outer reaches of space. So in order to reach Saturn, we're going to repeat this entire procedure from the beginning again. But this time we use Jupiter's gravity as our slingshot to fling us even further outward dramatically. If we maintain our velocity, we'll be moving too fast for Jupiter's gravity to capture us permanently. But it will still have enough power to bend our path significantly as we fly past. It's kind of like rolling down a hill gaining speed, then getting looped around a sharp turn. Then you find yourself climbing up the opposite hill, losing all that speed you just gained previously. So all the extra velocity we gained by approaching Jupiter, we lose as we fly away. The hills kind of cancel each other out, leaving us with the same speed we started with. But the curve in our path has now pointed us directly at the planet Saturn ahead. Our biggest challenge now becomes just covering the sheer distance between these two gas giants successfully. When you look at a typical illustration of the solar system, Jupiter and Saturn appear close together. But that's only done for the sake of making a diagram that fits on a single page. In reality, Saturn is almost twice as far away from the Sun as Jupiter orbits currently. So we end up spending several years just coasting through empty space between the two planets. But eventually, the magnificent rings of Saturn begin coming into view through our observation windows slowly. Now, even though Saturn is really big, similar to Jupiter in overall size and appearance noticeably, it's actually a lot less massive, with only about 1/3 the weight of its neighbor. That means only about 1/3 the gravity pulling on our spacecraft as we approach its orbit. So we don't have anywhere near as much pulling force that we need to push against. That makes for a relatively easy maneuver to slow our vehicle down and become captured in orbit. That extra coast time extends our journey from Earth to Saturn out to nearly 7 years. And now the time has come to set our sights on Uranus, the 7th planet from Sun. As you might expect by now, we're going to repeat our gravity-hopping procedure from inner worlds. We'll use Jupiter as our big kicking-off point to launch ourselves into deep space again. We can also add Saturn to that list and use its gravity to curve our path again. But there's a significant catch here that complicates our plans for reaching Uranus in our lifetime. In order to use multiple planets as slingshots in a sequence like this, they must be aligned. They all have to be in very specific positions when you launch from Earth initially planning, lined up in a way that lets you swing from one planet to the next like beads. Unfortunately, that alignment doesn't happen often enough to rely on for mission planning purposes, realistically speaking here. The Voyager probes, launched in 1977, took advantage of this rare planetary alignment successfully back. That configuration made the grand tour of the solar system possible, visiting 4 outer worlds sequentially. But that opportunity won't come again until the year 2152, which is unfortunate. And by that time, we'll probably have warp drive that can take you anywhere instantaneously anyway, so it won't even matter for future generations of space explorers who follow our footsteps eventually. But there's still hope for Uranus in our lifetime if we're willing to be patient here. There is a launch window opening in 2031 that would allow a spacecraft to proceed, using a gravity assist around Venus and Earth to launch itself out on a path outward. It would intersect Uranus in about 13 years, which isn't too bad considering the immense distance. That's not unreasonable considering that Voyager 2 probe took about 9 years to get there originally. And Voyager had the benefit of that very special planetary alignment we discussed earlier in detail. Now Neptune is the furthest planet from the Sun, at least according to current definitions anyway. At least that's what they want you to believe, depending on who you ask about classifications. And the distance we're looking at now is kind of unfathomable to the human mind, truly. It's 30 times further away from the Sun than Earth orbits, making it incredibly remote always. It's 6 times further than Jupiter, which already felt like deep space when we arrived there. Out here, light from the Sun barely even registers as more than a bright star. After using a gravity assist from Uranus, it took the Voyager probe another 3 years coasting. About 12 years in total flight time from Earth to Neptune's orbit in deep space. But those probes didn't have powerful engines on board for course corrections or velocity adjustments regularly. They relied entirely on gravity to steer them out this deep into space without fuel. So over such a long distance, our spacecraft could probably start catching up using engines periodically. And that makes our travel time more like 15 years at the most to reach Neptune. Now technically, Pluto is not a planet according to the International Astronomical Union's current definition today. It depends on who you ask, really, and what classification system you prefer using personally. But let's go there anyways, because it's cool, and because there has been one mission. It was a probe called New Horizons that successfully flew past Pluto in 2015 spectacularly. The only problem was that by the time it got all the way out here, it had nowhere near enough fuel remaining to slow down and get caught in orbit. You see, Pluto travels around the Sun at about just 17,000 kilometers per hour slowly, while New Horizons was traveling at about 83,000 kilometers per hour by arrival time. That speed differential made orbital capture physically impossible with remaining fuel reserves available to mission planners. By using this high-speed strategy, the probe was able to fly from Earth to Pluto. It completed the journey in just about 10 years, which sounds impressively quick for such distance. If we wanted to continue our streak of arriving and orbiting every planet and non-planet, then it would be closer to 20 years before we actually arrive at Pluto to stay. Okay, so we've just visited 8 planets plus 1 dwarf planet, completing our solar system tour. How long does that all take if you add up every journey we've completed so far? Well, if you combine it all, we've clocked just over 64 years traveling between destinations. Probably the kind of endeavor that you'd want to start young or choose your favorite strategically wisely. But if you want to start learning about every planet in detail right now today, so reaching Uranus demands we repeat that gravitational hopscotch routine we perfected traveling from inner worlds to outer ones systematically before. Jupiter serves as our primary launch platform, flinging us deeper into space than we've ventured during any previous leg so far. Saturn can join that equation too, bending our trajectory once again toward the solar system's frigid outer boundary zones ahead. But here's where mission planning hits a wall that no amount of engineering brilliance can overcome through clever maneuvering alone. Using multiple planets as sequential slingshots requires them all sitting in very specific positions when you initially leave Earth behind. They must align like cosmic dominoes arranged perfectly, so one gravitational kick flows seamlessly into the next encounter down the line. Unfortunately, that celestial alignment happens about as often as total solar eclipses visible from your hometown, specifically during your lifetime realistically. The Voyager probes launched back in 1977 caught a rare planetary configuration that won't repeat for generations ahead. That lucky geometry enabled the legendary Grand Tour visiting Jupiter, Saturn, Uranus, and Neptune in one continuous journey through space. But that same opportunity won't come around again until the year 2152, which feels impossibly distant now. By that point, humanity will probably have invented warp drives or wormhole generators, making our current propulsion methods look quaint. So worrying about optimal planetary alignments a century from now seems like a pointless exercise in hypothetical mission planning today. But hope remains for reaching Uranus during our own lifetimes, if we're willing to accept longer travel times without complaint here. A launch window opens in 2031, allowing a spacecraft to use Venus and Earth for gravitational boosts outward initially. That trajectory would intersect Uranus roughly 13 years after departure, which sounds reasonable given the staggering distance we're attempting to cross. Compare that to Voyager 2, which needed only 9 years to reach Uranus using that special planetary alignment we discussed earlier. An extra 4 years doesn't seem like such a terrible price to pay for visiting a world most humans will never see. The ice giant awaits our arrival, patiently rotating on its side with those faint, ghostly rings barely visible against the void. Neptune represents the furthest planet from the Sun, according to every astronomical chart published since Pluto's controversial demotion years ago now. At least that's the official story, depending on which planetary scientist you ask, and what mood they're in that day. The distance we're contemplating now exceeds anything the human mind evolved to comprehend through everyday experience with terrestrial measurements nearby. Neptune orbits 30 times further from the Sun than Earth does, making it almost incomprehensibly remote from our perspective looking outward. It sits 6 times beyond Jupiter, which already felt like venturing into deep space when we arrived there years ago earlier. Out at Neptune's distance, sunlight barely registers as more than an unusually bright star among thousands scattered across the black sky. After executing a gravity assist at Uranus, the Voyager probe needed another 3 years just coasting through emptiness to reach Neptune. That brought total flight time to roughly 12 years from Earth launch to final planetary encounter in the outer solar system. But remember, those probes carried no powerful engines capable of sustained acceleration or significant course corrections during flight at all. They relied entirely on gravitational interactions to steer themselves deeper into space without burning precious fuel reserves along the way consistently. Over such enormous distances, our spacecraft, equipped with modern propulsion systems, could probably close the gap faster than Voyager managed. That brings our realistic travel time estimate down to approximately 15 years maximum for reaching Neptune and establishing stable orbit there. Now, Pluto technically isn't classified as a planet anymore, according to the International Astronomical Union's updated definition from 2006. Whether you accept that reclassification depends entirely on who you ask and how strongly they feel about planetary definitions today. But we're going there regardless because Pluto remains fascinating and because one NASA mission successfully completed the journey already recently. That probe was named New Horizons, and it launched in 2006, racing toward the outer solar system's edge. The spacecraft performed a spectacular flyby of Pluto in 2015, capturing stunning images that transformed our understanding of this distant world. But New Horizons carried a critical limitation that prevented it from doing anything beyond taking pictures during that brief encounter window. By the time the probe reached Pluto's orbit, it had nowhere near sufficient fuel remaining to slow down for capture. Pluto creeps along its elongated orbit at merely 17,000 kilometers per hour, moving slower than any planet we visited previously. Meanwhile, New Horizons screamed past at 83,000 kilometers per hour, making orbital insertion physically impossible with remaining propellant available. That massive velocity differential meant the probe got exactly one shot at gathering data during its closest approach to Pluto. Everything had to work perfectly during those few precious hours when the spacecraft flew past this remote world at breakneck speed. The mission succeeded brilliantly within those constraints, but it highlights the fundamental challenge of reaching such distant destinations and actually staying there. By adopting New Horizons' high-speed approach strategy, the probe completed its journey from Earth to Pluto in approximately 10 years. That timeline sounds impressively quick, considering Pluto orbits nearly 40 times further from the Sun than Earth does on average. If we wanted to maintain our perfect record of arriving and orbiting every world instead of just flying past them, then we'd need closer to 20 years before actually establishing stable orbit around Pluto and its 5 known moons altogether. That extended timeline accounts for the extra fuel required to slow down sufficiently for gravitational capture by such a small world. Pluto's gravity barely registers compared to the gas giants we encountered earlier, making the deceleration phase even more challenging than usual. So we've just completed a grand tour visiting 8 recognized planets plus 1 controversial dwarf planet spanning the entire solar system. Adding up every individual journey we've undertaken reveals a total elapsed time exceeding 64 years of continuous interplanetary travel overall. This represents the kind of lifelong commitment you'd want to begin young, or choose your favorite destinations strategically based on priorities. Starting such an expedition in your 20s might allow you to reach Neptune before your 90th birthday, if everything proceeds perfectly. But mechanical failures, radiation exposure, and 1,000 other hazards could end the mission prematurely at any point along the way. The pioneers who attempt this journey will need patience, perseverance, and acceptance that they may never see Earth again. Yet despite those sobering timelines and risks, something profound calls us outward, toward those distant worlds waiting beyond our atmosphere. Every planet holds secrets about our solar system's formation and evolution that we can't unlock from Earth alone anymore. Mercury's cratered surface tells stories about violent impacts that shaped the inner solar system during its chaotic youth billions ago. Venus teaches harsh lessons about runaway greenhouse effects and what happens when atmospheric chemistry spirals out of control permanently. Mars whispers possibilities of ancient oceans and perhaps even life that once flourished before the planet lost its atmosphere. Jupiter, Saturn, Uranus, and Neptune reveal dynamics of gas giant formation and the complex dance of dozens of moons orbiting around. Even Pluto, way out on the frontier, shows us how worlds form and survive in the cold, dark edges. If you want to start learning about every planet in detail right now, today, then there's no better place than here.